Hey everyone, Mr. Hauk here. In today's video, we're going to be looking at graphs of trigonometric functions and trying to write the equation based off the appearance of the graph. Let's go ahead and get started. We're going to start today by talking about the relationship between sine and cosine. Notice that in the graph provided, cosine is the graph in blue, so y equals cosine of x is in blue. And notice that sine is the graph in red. One way that I always remember this is that the parent function of sine always passes through the origin, the parent function of cosine always passes through 0, 1. So one thing that we might try to figure out here is how are sine and cosine related to each other? Well, notice that if I took the blue graph and simply shifted it to the right by pi over 2, going from 0 to pi over 2 here, that the blue graph and the red graph would actually overlap each other. That means that cosine and sine would overlap. So the way that sine and cosine are related is that sine of x is equal to the cosine of x shifted to the right pi over 2 units. Okay. Now typically when we think minus in terms of left and right, we think minus means go to the left. But recall from algebra that when we were doing a horizontal transformation, if you have the input variable x minus a number, it's actually going to move to the right horizontally. If you have the input variable x and it was plus a number, it would actually shift to the right. Or sorry, plus would be shifting to the left. Okay, so this is our relationship between sine and cosine. And we're going to use this relationship in just a minute here. So we want to talk about transformations of these trig functions. And for sinusoidal functions, which recall are sine and cosine functions, this is one of the key formulas that we're going to be using to talk about trig transformations. So I'm going to go ahead and box that. So notice we have, and I'm going to zoom in on it, y equals a times sine of b x minus c plus d. And each one of these variables, a, b, c, and d, each plays an important role in the transformation. So we discovered in the previous video on amplitude and period that a, if we took the absolute value of a, represents the amplitude, and that amplitude affects the height of the graph. We also saw in the previous video that the number you multiply by x, which in this case is b, affects the period. And we saw that when b is between 0 and 1, the graph actually stretches horizontally, and that if b was larger than 1, the graph would actually shrink horizontally. The variables c and d are both new to us. We haven't really investigated them yet. But what c represents is a horizontal shift, or a phase shift. And what that means is that it's going to take our trig function, it's going to shift it to the left, or it's going to shift it to the right. And d represents a vertical shift. And all that means is that we're going to take our trig function and either shift it up, or we're going to shift it down. Now, since we just found out the relationship between sine and cosine, and we basically saw that sine and cosine can be made equal to each other by shifting the cosine function to the right by pi over 2, that means that all of these key characteristics also apply to the cosine function, okay? They also apply to tangent with the exception of the period. We saw in the previous video that the period for tangent can be calculated with pi over b instead of 2 pi over b. This is because the period for the parent tangent function is pi instead of 2 pi. Okay, so let's go ahead and start investigating some of these characteristics here. We're going to be using the parent function for sine to explore all the different trig transformations. So when looking at the parent function of sine, let's record a couple things that we know. Number one, we know that the period for the parent function of sine is 2b. So I'm going to go ahead and say that the period, or sorry, not 2b, but is 2 pi. And what this tells us is that if the period is 2 pi, it automatically implies that b is going to be equal to 1. Okay, and we can see that right here because the coefficient, the number being multiplied by x, is just a 1. We also can see from the parent function that the number in front of sine is an implied 1 as well. So we know that the amplitude is equal to 1. And we can see that because the distance from the midline to the maximum value and the distance from the midline to the minimum value are 1, and that's what the amplitude represents. Since we were talking about the parent function, we know that there have been no horizontal or vertical shifts. So we also know that c is equal to 0, hasn't been moved left or right, and we also know that d is equal to 0 because it hasn't been moved up or down. C representing a shift left or right, d representing a shift up or down. So let's see if we can figure out what's different between our parent function on the left and this green function on the right. So when I look at this, the big difference that I'm seeing is that the function on the right seems to be taller in both directions. And if we want to think about the characteristic that affects height, well, if we look at our first page, amplitude is the characteristic that affects the height of our trig graph. So the amplitude is different. Well, let's try to figure out how different. If the amplitude of the parent function is 1, let's try to find the amplitude here of the transformed function. Well, we have our midline is right here at the x-axis. And if we try to find the amplitude, the distance from the x-axis to the maximum value is 3, and the distance from the midline to the minimum value is also 3. So this tells us that the amplitude is 3. And if the amplitude is 3, that means that the a value is going to be 3 here. So what that tells us is that the equation of this new graph is y equals 3 sine of x. All right, let's try another example. So again, we're looking at the parent function for sine, and we want to see what changed from the parent function to the new function on the right in green. Well, the first thing that I immediately notice is that the period seems to be much longer. So instead of the period being 2 pi, we can see here that the period is 4 pi. So let's take note of that. So t equals 4 pi. And if we want to think to which of the variables a, b, c, or d is being affected by the period, well, we can see right here that the period is affected by b. So let's go ahead and try to figure out what b would be. Since we know that the period is 4 pi, and we know that the period is equal to 2 pi over b, we can substitute t with 4 pi, and we can rewrite this as 4 pi, the period here, is equal to 2 pi divided by b. Now we can just simply try to solve for b. So let's go ahead and multiply b on both sides. And what this gives us is b times 4 pi equals 2 pi. And then by simply dividing the 4 pi on both sides, we get that b equals 1/2. Okay? So again, the period is different here. And because the period was 4 pi, we found out that the b term is 1/2. So that means our new equation would be y equals sine of 1/2 x, which is the same as x over 2. All right, looking at our next example, again, we're looking at the parent function of sine, and we're trying to figure out what happened in the graph to the right. Well, it looks like the period is still 2 pi, because from pi over 2 to 5 pi over 2, it's still a 2 pi period. The amplitude is still 1, but if we look at the difference here, it looks like we took the parent function and we shifted it to the right by pi over 2. So the graph has been shifted right by pi over 2. Okay, well, if we think back to which variable represents a right or left shift, a horizontal shift, that's going to be the variable c. So because we have been shifted to the right by pi over 2, the way that we would write this equation is that c would equal pi over 2. Now here's where we have to be a little bit careful. If you look at your equation, notice that there is already a negative sign in front of c. So since c equals pi over 2, we would end up having x minus pi over 2. Okay? So let's go ahead and write that down. We would have y equals the sine of x minus pi over 2, because the c term is pi over 2. Looking at our next example, again, we have the parent function of sine, and we want to find out what's happening in the graph to the right. Well, once more, notice that the period is still 2 pi, the amplitude has not changed, the amplitude is still 1. However, it looks like the original function, which notice the parent function of sine starts at 0, 0, it looks like it's been moved up by 2 units because now the function is starting at 0, 2. So this function has been shifted up by 2. Well, when we talk about a shift upwards, that means we have a vertical shift. And vertical shift is represented by the variable d. So what this is telling us is that d is equal to 2. If I wanted to write the equation of the transformed function, we have the original parent function sine of x plus 2, because if we look at the equation for the transformation, vertical shifts are added or subtracted at the end. So we have sine of x plus 2. Next, we're going to look at these 3 examples. And notice that for the functions on the left, they're the parent functions that we've become familiar with over the last few days. So each one of these, this one right here, this is y equals sine of x, the parent function for sine. The second graph on the left is y equals cosine of x, parent function for cosine. And the third graph on the left is y equals tangent of x, the parent function for tangent. So if we look at the differences between the graphs on the left and the graphs on the right, what we're going to notice is that all the y values have been multiplied by -1. For example, pi over 2 comma 1 changed to pi over 2 comma -1. 3 pi over 2 -1 changed to 3 pi over 2 positive 1. So what ended up happening is that this graph was multiplied by -1, which caused a reflection across the x-axis. Notice that pi over 2, if we reflect it across, or this pi over 2 comma 1, if you reflect it across the y-axis, or the x-axis rather, you get pi over 2 -1. Let's see if the same thing happened with cosine. We have 0 comma 1. If I multiply the y value by -1, I go from 0, 1 to 0, -1. And we can see the same thing happening here. We have pi comma -1, you multiply the y value by -1, and you get pi comma positive 1. Even with the tangent values, and these ones are a little bit harder to see, but let's say we look at something like this. This looks approximately equal to 1 comma 2, and over here it seems that we have 1 comma -2. So all the y values have been multiplied by -1. So let's record that here. We're going to say the graphs were reflected across the x-axis. And this simply means y values multiplied by -1. So what would these transformed functions look like? Well, it's actually pretty simple. If the y values have been multiplied by -1, we simply go from y equals sine of x to y equals negative sine of x, y equals cosine of x to y equals negative cosine of x, and from y equals tangent of x to y equals negative tangent of x. So what we want to do now is we want to look at these 4 practice problems, and notice that in the instructions, we are told that these graphs have undergone multiple transformations. So we're not just dealing with one transformation at a time, we're dealing with two or more transformations at a time. We want to take these graphs and we want to write the equation of the trig functions based on the graph, and then use Desmos to check our answers. So beginning with the top left graph, let's notice a few things here. Number one, let's try to find the period. So I'm going to highlight one complete cycle, and it looks like the cycle is going from 0 to 2 pi. So the period is equal to 2 pi. Well, we know that for both sine and cosine, the parent functions had a period of 2 pi. And if this still has a period of 2 pi, that means the period hasn't changed. So this is telling us that the b term is going to be equal to 1. Because if we think about the sine and cosine parent functions, the b term is already equal to 1. Okay, so we know b is equal to 1. Let's think about what the a term might be. Well, we know that the a term represents the amplitude. And if we think about the amplitude here, well, let's see where our midline would be. It looks to me like the midline is going to be at -2, and the distance from the midline to the bottom is 4, and the distance from the midline to the top, or the maximum, is also 4. So our amplitude is a positive 4, which means our a term is a positive 4 as well. Now let's think about our c term and our d term. Well, the c term says, what was the horizontal shift? Well, if we think about the sine function, the cosine function rather, the cosine function starts at 0, 1. Well, we still have 0, 2 as a point, so it doesn't look like the graph has been shifted left or right at all. It's only been shifted up. So our c term, the horizontal shift or the phase shift, is 0, because we haven't shifted left or right at all from the original cosine function. However, we just noticed that the d term indicates that we have some kind of vertical shift. Well, let's think about what the vertical shift might look like. Notice that if we think about the original cosine function would have started at 0, 1. But if the amplitude is positive 4, when that 0, 1 would have got multiplied, it would have moved all the way up to 0, 4. But then the vertical shift takes that point and moves it down twice. Okay? So it's looking like our vertical shift is down 2, which would be a -2. Another way to look at it is where the midline is. Typically, the midline for cosine, the parent function of cosine, would have started at the x-axis. And it looks like the midline has been shifted down twice. So that's telling us that the vertical shift is a -2. Putting all of this together, let's now write the transformed function. So we have y equals a cosine b times x minus c plus d, and this is going to tell us that y equals 4, because a is 4, cosine of 1x. Well, we're not multiplying, we don't need to write the 1, because we know that the 1 it's understood, it's implied there. We know that c is going to be 0, so we don't have to add or subtract anything, so this will just be an x. And then d is -2, so -2. So 4 cosine of x minus 2. Okay, now let's double check that with Desmos real quick. All right, so I've already got my graph in terms of pi. Let's go ahead and graph y equals 4 cosine of x minus 2. And let's see if we can notice some of these key points here. I can see 0, 2, just like we have right here. Oh, that looks terrible. We can see 0, 2 right there. We can see pi comma -6, just like we can see right here. I can see 2 pi comma 2, which is right there. So our points are lining up. This is going to be the correct graph. All right, let's try another one. Once again, we want to try to find the a, b, c, and d term. And looking here, let's start with the amplitude. So if I go and look for the midline, it's looking like the midline is right here. This is the line that goes through the middle of the graph. And if I look at the amplitude here, we have to go down 3 units to get to the minimum, and we have to go up 3 units to get to the maximum. So the amplitude is going to be 3. So that tells us that the A term is a positive 3. Now let's think about the period. So typically for a cosine or a sine function, the period is going to be 2 pi. If I look at the period here, this period is pi over 2. So that's going to help us solve for the B term. So if the period is pi over 2, and we know we're dealing with either a sine or a cosine function, that means we can take that period, pi over 2, and set it equal to 2 pi over b. So we need to think to ourselves, what would b have to be in order for this to be a pi over 2? Well, there's a couple things that we can try. We can try to multiply b on both sides. So let's go ahead and do that. So times b times b. And this is going to give us that b times pi over 2 is equal to 2 pi. And then we can divide both sides by pi over 2. Okay, so this is telling us that b is actually equal to 2 pi over pi over 2. We can do our whole keep change flip, so 2 pi times 2 over pi. Well, notice that the pi's will cancel. You get 4 pi over pi, which is just equal to 4. So we're finding out here that the b term is equal to 4. Okay? Now let's think about the c term and the d term. Well, the c term would be a phase shift or a horizontal shift, but notice that if we think about cosine starts basically at 0, 1. Well, we have this 0, 2 right here, so we can see that there's been some kind of vertical shift, but there hasn't been a shift left or right at all. So the horizontal shift or the phase shift is going to be 0. But now let's figure out the vertical shift. We know that for both cosine and sine, at least the parent functions, that the midline usually starts at the x-axis. Notice that the midline here has been moved down 1, so we have a vertical shift of -1. So let's try to figure this out here. We're going to use a cosine function because we have this point right here being on the y-axis, and it's not going through the origin. So we would say that y equals a cosine of b times x minus c plus d. We know that a is equal to 3, so we'd have 3 cosine. We know our b term is going to be 4. Our c term is 0, so we have to worry about adding or subtracting anything. And we know that our d term is -1, so this would be a -1. So we have y equals 3 cosine of 4x minus 1. And once again, let's graph that in Desmos just to make sure that everything is working. All right, so let's hide that graph. And now we're going to try y equals 3 cosine 4x minus 1. And let's see if we can see some of these key points here. So we have 0, 2. There's 0, 2. We have a pi over 4, comma, -3. Well, there's pi over 4, or sorry, -4. There's pi over 4, comma, -4. And we'll just check one more point. There's pi over 2, comma, 2. And we can see that on the graph as well. So that is a correct equation for that graph. All right. The last example we're going to do here in the notes in this video is example number 3. And notice that this time it's pretty clear that this is a tangent function. So let's see what we can pick out here. Number 1, let's think about the amplitude. So the amplitude is how are we multiplying by? Well, typically for a tangent function at pi over 2, we would get a y value of 1. Notice that now we're getting a y value all the way at +4. So it looks like the function is being multiplied by 4. So we would say that the a value, or the amplitude, is equal to 4. Now we want to think about the period. Well, typically the period of a tangent function is pi, but we can see here that the period is actually 2 pi for this one. So if the period t is equal to 2 pi, we know that for tangent, the period, let's go back to there real quick, we know that the period will be equal to pi over b. So we just need to figure out what would the b term be to make the period 2 pi. Well, let's multiply both sides by b. This will get us b times 2 pi equals pi. You could then divide both sides by 2 pi. And this tells us that b equals 1/2. Now, one of the nice things about this is that we haven't shifted left or right at all. If you think about the parent function of tangent, we go through the point 0, 0. That hasn't shifted left or right. It also hasn't shifted up or down. So the horizontal shift or the phase shift is 0, and the vertical shift is also 0. So the equation here for tangent would be a tangent b times x minus c plus d. And just plugging in our pieces, we have y equals 4 tangent of 1/2 x, which is the same as x over 2. C and d don't really matter here, so this would be our equation. One last time, let's check with Desmos and see if this checks out. So we're going to say y equals 4 tangent of x over 2. And let's see if we can notice some of these key features. All right, we see that it's going through the origin 0, 0. That's good. We can see it's going through 2 pi comma 0. That's good. Those are these points right here. And we can also see pi over 2 comma 4. Well, here's pi over 2 comma 4 right there. So this is correct. Our points are checking out. So this is indeed the correct equation. I've put a challenge problem on here, number 4. I'm not going to go over this right now. I'm going to go over this in the live session in class. I encourage you to try the challenge problem. It's fairly difficult, but if you can figure it out, you're on top of the game here.